Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about supernova. And supernovae are exploding stars, supermassive stars that are at the end of their life, and they go out with a bang. So let's see how they work, because we talked about large stars and how they lived last time, and we found that they actually don't live as long a lifespan as low-mass stars. So let's see what the big boys do. So the endpoints of various stars of solar mass levels is kind of summarized here. This comes from one of the Paterson type textbooks. And if it's really small, less than 8% the mass of the sun, it does not do anything dramatic. They're brown dwarfs. And they basically they never initiate hydrogen fusion. Between about 8% of the mass of the sun, about a quarter of the mass of the sun, the final end state would be a star that has completely converted itself from hydrogen into helium, and it becomes a helium white dwarf. Somewhere between, say, about a quarter of the mass of the sun and about 4 to 8 times the mass of the sun, this table I think is a little bit old, the star ends up as a white dwarf, a carbon-oxygen white dwarf. And if it's much, much larger, then about 4 to 8 times the mass of the sun, about 12 times the mass of the sun, at the time of main sequence burning, then it'll end up with a neon oxygen white dwarf. And if it's larger than that, with 12 solar masses, you get a supernova. And a supernova doesn't produce a planetary nebula or a white dwarf. It produces something completely different. So let's see what that looks like. Last time we talked about the last days of a supermassive star, and where we ended it with, where massive stars go through these huge, fast burning. Burning now means fusing hydrogen into helium or some element into another element to liberate energy. And very massive stars, roughly at least 8 to 10 times, at least 10 times the mass of the sun, they burn hydrogen into helium for only about 10 million years, a very short time period compared to the sun's 10 billion year rough lifespan, which is about 1,000 times longer. And once they do that, they only burn helium for about 1 million years, convert carbon into oxygen and neon for only 1,000 years, fuse neon into oxygen for only about 10 years, oxygen into silicon only for about a year, and then the final stage of burning silicon into nickel and iron only lasts a day. Now this means that down in the core of this nested onion skin sort of thing, way down in the core, a very, very large inert iron and nickel core is building up rapidly and compressing and starting to do a major compression, as it's not producing any energies, but it does release energy by compressing. So it's releasing some of its heat by simply releasing it through gravitational compression. And that's what the iron core is doing. So at the end of this day, there's all this shell burning, and we've seen burning again here means fusion. Hydrogen fusion, helium fusion, carbon, neon, oxygen, silicon, and fusion all the way down into the core. The exterior of the star is now extraordinarily massive. It's a red supergiant or a red giant or maybe even a blue supergiant, but it's definitely a supergiant star. And the size of the star now has expanded out to about 5 astronomical units, or almost the orbit of Jupiter or larger. But the core is extraordinarily compact, and that's where all the action is. The outer envelope is just primarily hydrogen and helium, but there's practically no mixing between the outer envelope and the inner core. So we gotta now we have a touchstone that we have to actually understand for what's going to happen next. And what we've really been talking about the entire time is how much energy is liberated by combining nuclei together. And that's what we call the binding energy per nucleon. And this graph, which comes from data that I downloaded from the International Nuclear Structure and Decay Data Network, which is a subdivision of the International Atomic Energy Agency, which tries to help people not explode nuclear weapons in various countries and so forth. That's one of the things they do. Anyway, they do have a very fascinating set of data about the nature of atomic energy and nuclear energy. And so I downloaded all the data and found how the binding energy per nucleon is in mega electron volts, which is a little tiny amount of energy, but in terms of nuclei, it's pretty large. The number of nucleons on the bottom shows how many protons and neutrons there are in the nucleus. So those were the nucleons we're talking about, protons and neutrons. And notice the graph has a peak right around 50 or 60, right? Just north of 55 or 60. And there's some other residual peaks off to the right, and there's a big drop off to the left. Everything that we've been talking about with the little stars up to this main sequence stars takes tiny nuclei, which would be on the lower left with a number of nucleons. One is hydrogen, which is a proton, and the number of nucleons builds from 1 up to 4. And in fact, I'm just going to move my mouse across and show you where helium is. And right there, where I put my helium, where I put this on there, that is helium. Helium nuclei are incredibly well bound. So if you put helium to get hydrogen together to helium, you get a big jump. So there's an enormous, enormous jump that happens when you bind hydrogen into helium. All right, so this graph shows how much energy is liberated when you put all these protons and neutrons that into a nucleus, or how much energy you have to provide to the nucleus to tear them apart. So it's interesting to note that this graph has a peak, and it drops off to the right for very, very large nuclei, and it drops off to the left for very small nuclei. So this means that we will have what's called a nuclear impasse. The fusion of light in elements, anything less than iron, gives off energy due to fusion. So we see in this graph below that hydrogen, or H1, which is just a proton, gives off energy by fusing hydrogen to deuterium, H2, which we see down below. And that's what we've known that, though, since we talked about the proton-proton chain. And we also knew that hydrogen fusing to helium gives off a lot of energy, because there you see He4 in this graph, and that gives off energy. We also know that fusing helium into carbon gives off energy, but not as much. See the difference in energy between helium-4 and carbon-12? It's not as much as the difference between hydrogen-1 and helium-4. There's a large amount of energy that's given off by fusing hydrogen-helium, but not as much from helium to carbon, and the step is even smaller from carbon to oxygen. In fact, if you look, you can see that as you go up and up and up to the peak at iron 56, that each step is progressively smaller. You get less and less and less energy out of the reaction by combining something with carbon-12, combining it with a helium nucleus to form oxygen-16. You don't get as much energy. In fact, the energy difference to get it from oxygen-16 to iron 56 is very small. So therefore, there's less. This is what we were talking about in the last time, is as it progresses, each successive step provides less and less and less energy output. It also takes more energy to do it because these things have protons, and the protons push against each other for the electrostatic force. And so you get less and less energy out. The nuclei are bound less and less strongly, which means it takes less and less energy in order to rip them apart. And if you fuse but the general trend of this whole graph is that if you fuse elements lighter than iron together, you do get energy out. And if you have and to get elements heavier or more massive than iron with more nucleons in the nucleus of the nucleus, then it actually has less bound. So if you look at uranium-238, we have on the cross there, we have on the right-hand side, we see that it is less bound than iron-56, meaning it has less binding energy per nucleon. And so just piling stuff on top of it means it takes energy to put these things together in order to actually create uranium-238. You don't liberate energy, you absorb energy in order to go there. We see that helium to carbon gives off energy because you go up. Carbon to oxygen gives energy because you go up. And oxygen all the way up to neon and magnesium all the way up to nickel gives energy all the way up to iron 56. And below that, fusion gives off energy. But if you fuse elements together and try to go more massive than iron, it takes energy because the binding energy is less, so you have to push it together to keep it together. That's a better way of talking about it. In fact, another way to look at it is we use uranium in our fission nuclear reactors in order to get electric power, and we get that power by uranium radioactively decaying down to lead, and that gives off energy. And so uranium decaying to lead, which is about halfway up, or more than halfway up that from the far right-hand side to the left, towards the peak, gives off energy. So above iron, fission gives off energy, and to get things more massive than iron, it takes energy. So this is a more detailed view. And I was poking around on the internet to try to find a little better view, but this is not very clear. And what I did then is I decided to try to zoom in and show you what's really there, but it's really not clear. We've got iron 56 and nickel 58 at the top. We have strontium 6088 and scandium and cesium, and there's polonium, lead 208 way down there. But these graphs are kind of hard to read. I'll grant that because they're low resolution on the internet. So again, I went back to the IAEA website and grabbed just that data to see what the most bound nuclei are. And we'll look at the top peak. We see there's three nuclei that are the most bound. And iron 56 is the leftmost of the three top ones. Nickel 58 is just a little bit more bound, and then there's nickel 62, which is also just a little bit more bound than nickel 58. So anything below this peak, you get energy by fusing things from the left-hand side of the peak up to the right-hand side of the peak. And the typical fusion means take an element, take a nucleus, and either slam a proton into it or slam a helium nucleus into it. That tends to be the dominant reaction that you would do in order to do fusion. You sometimes have like two carbon nuclei slamming together, and that falls apart and gives off stuff. But it's very easy to say, let's get a helium nucleus because it's lighter than a carbon nucleus and spin it up really fast so they can smack into stuff. Be that as it may, however many ways there can be, because each one of these dots is a separate nucleus. So there's lots of different nuclei, lots of different isotopes of various nuclei. But you get them by doing fusion or then radioactive decay by fission. So what happens in the center of a star? In the center of the supermassive star, the iron core is going to grow and grow until by the silicon fusion happening above it, until the mass becomes about somewhere between 1.2 and 1.4 solar masses. And then the core will collapse under its own mass because it exceeds the Chandrasekhar limit for it exceeds the limit that a white dwarf can have before it will explode. So a white dwarf is basically forming an electron degenerate core in there. It can't be supported by electron degeneracy. And all of a sudden, the core collapses down rapidly and heats up amazingly. And it gets up to about 10 billion Kelvin, and the density is about 10 billion grams per cubic centimeter. So one sugar cube would weigh 10 million kilograms, or that roughly translates into a few 100,000 tons. So we have a sugar cube weighing hundreds of thousands of tons. That's a lot of weight, and that's how dense the core becomes. However, even though it's that dense, it is still a gas because it is so incredibly hot. And way down in the center, it's incredibly turbulent because the star's core is rotating, and as it rotates, it spins everything around, and so you got all this crazy mixing happening. And even though the core is there, it's not moving. It's the star itself is spinning. When it's that hot, the energy is primarily in the form of kinetic energy of the nuclei bouncing into each other, and that's at roughly the same temperature as the light. So there are gamma ray photons that can't go very far because the density is so incredibly high that they actually equalize the temperature with the material around them. So everything is the same temperature, both the light, the profile of the light in the black body spectrum, as well as the nuclei that are zipping around. And that has a number of results. Once you get enough of the energy in the form of light, then the light itself has enough energy in form of a number of mega electron volts to actually disintegrate the nuclei. Remember, those nuclei have binding energies of iron is roughly about 8.5 or 9 mega electron volts. And once the temperature of the center of the area exceeds about 10 billion Kelvin, which is really high, that's 10 billion, right? 10 billion. Once it exceeds that, then a significant fraction of the energy of the light actually has an energy on the order of about 10 or so mega electron volts, which is a very high energy gamma ray. So once these gamma rays go flying around, they can actually disintegrate the iron nuclei. And when the iron nuclei disintegrate, they absorb the energy of the light. And then that lifts the nucleus apart, giving the constituents its energy. And that binding energy then is absorbed out of the system. And so as as the nuclei now start to absorb the light and then break apart because of it, this is called photodisintegration. It removes the light and therefore removes the energy that supports it. It robs the core of energy. It robs the core of pressure because if it's hot, it has high pressure. Second, then the density continues to increase, and at this, because as everything's breaking apart, then there you have free neutrons and free protons. So as there's photodisintegration happening, it doesn't just break it into helium nuclei; it breaks it down into also protons and neutrons. That's very high energy light, and so now the protons and electrons are very close together. They can fuse together to form neutrons, and the neutrons then, of course, give off neutrinos. And neutrinos carry a tiny amount of energy, and as they carry a tiny amount of energy, they escape and they just leave because neutrinos don't see anything. Remember, we talked about the surface of the sun, deep, deep, deep in the core of the sun, where neutrinos just escape. The reactions occur in the sun and they don't even see anything. So the neutrinos get out of there, taking energy further away from the core, leaving it with no energy. So there's no energy to provide pressure against gravity, because remember, gravity is always working. So the neutrinos escape, carrying away more energy to provide the pressure, and then it collapses catastrophically. So right around this only lasts about a day, this whole event. And once the iron core starts to collapse, it begins at about something roughly the size of the Earth at a density of and the iron core collapses at about 100 million grams per cubic centimeter. And then a second later, this is almost free, it's faster than free fall. Actually, it is free fall given the gravitational pull that it is. In total free fall, it drops from 6,000 kilometers in size down to 50 kilometers in size in less than a second, at about a quarter of a second later. And then the density increases to almost 10 to the 14th grams per cubic centimeter, which is astonishingly high density. And that density is the same density as an atomic nucleus. So you can't really push the nuclei together anymore because now they're literally in contact. So the density raises in the core, and it has to stop because now neutron degeneracy comes into play, just like we talk about electron degeneracy in the center of the sun. That causes the helium flash in low mass stars. But with neutron degeneracy, that then says, I'm a neutron. I can't go on top of another neutron. I can't go inside another neutron. We can be right together. We can be next to each other. We can touch each other, but we can't be inside each other. So therefore, the neutrons don't have any place to go except stack up against each other, and they cannot compress anymore. So since they cannot compress, basically it makes a bounce. So then you have an enormous bounce off the core because material still is piling down on top of it. The core is now collapsing down to about 2.5 times 10 to the 14th grams per cubic centimeter, which is the density of an atomic nucleus. And the strong nuclear force now comes into play, which does all sorts of weird things. Strong nuclear force is really poorly understood. But what it does is it actually says that now you have gluons that are doing the interaction between the protons and neutrons, and that interaction is very powerful and keeps the nuclei from going on top of each other. So the inner 3/4 solar mass of the core, that just stops. So everything else starts to fall on top of it, and it springs back a bit, doing what's called a bounce. And so material still keeps falling on top of it, but now that core collapse is coming back up. And that creates a shock wave. That shock wave kicks out about a huge amount of energy, 10 to the 44th joules, which is the equivalent of about 100 billion suns. That all happens in less than a quarter of a second. And in about 20 to 40 milliseconds, which is the same time it takes you to snap your fingers, all the matter that is getting swept up by the shock wave there's a bunch of stuff that's falling down on top, and the shock wave's coming up, and it stalls because now you've got material coming up and material coming down. You've got a shock wave above it, and then the interior of the core, because protons and electrons are still becoming neutrons inside of that core as part of this compression. The neutrinos are still trying to get out, and they can't. So they basically they get trapped. Finally, it becomes dense enough for neutrinos to get trapped. And by trapped, I mean 1 out of every billion or so. The other 999 million get out. But 1 in a billion, considering how many neutrinos are coming out, that's enough to do it. Those neutrinos get trapped in the gas. They then heat the gas, depositing their energy through weak nuclear reactions inside of the gas, and that turns it, because it's uneven across there, because the because neutrino interactions are rare, so it's going to be an uneven sort of distribution. That leads to incredibly violent convection right above the core, which is trying to bubble away and turn itself into one big atomic nucleus. And that makes a new shock wave as the neutrinos now push the whole thing apart. About 300 milliseconds, which is just over a quarter of a second, which is also, interestingly enough, that's about as fast as your brain processes thoughts. 300 milliseconds. That's interesting to think. So as fast as your brain can process a thought, the shock wave reappears and smashes out through the star, pushing up against the infalling matter, creating massive amounts of nuclear fusion in the wake because of the high density and high temperature. That shock that comes back up, which is now a shock wave or an explosion wave, heats and accelerates the rest of the star, and the shock eventually breaks out through the surface, moving at almost 10% of the speed of light. And from a distance, we see a star that's now about the size of Jupiter's orbit explode. And that's what we call a supernova. And for a very, very brief time, within minutes, a supernova can outlast up to 1 to 10 billion times the luminosity of the sun for just a few minutes, and in fact much longer. And it can outlast an entire galaxy of stars in terms of its output of light. And the outer envelope is then blown off into space along with much of the core and accelerated to a fraction of the speed of light. So this is going 1/30th of the speed of light. That's pretty fast. And that's a really fast shock wave. It's not a pretty thing. If you were next to it, you'd be dead. It doesn't matter how close you are, you'd be dead. You can't be Superman, you'd be dead. If you were within a light year, you'd be dead. That's just how this all works out. And, well, you're not going to be there, and they're never going to do an episode of Star Trek, and I'm even sure Doctor Who would lose it on that one. Anyway, the gas will expand, eventually cooling off, leaving only the core behind. And we see in the background here a galaxy that has a supernova in it. We see the supernova on the outskirts of this galaxy. And notice how it's almost as bright as the core of the galaxy. This is a dimmer supernova, but it was seen around that galaxy. In fact, you could think it might even be brighter than the core. And remember, the core of the galaxy is composed of maybe tens of billions of stars itself. So one star is much brighter than maybe tens of billions, 50 billion stars that are deep in the core of this galaxy for just a few months. And that's what a supernova is. And this has a name, 1994D, because it was seen in 1994, and it was the fourth one observed in 1994. So that's why it's called Supernova 1994D. Then this was one that I saw in 2014. This happened in the nearby galaxy M82. It was a different kind of supernova, but still the point's the same. It was a super bright star, and that bright star appears inside of the disk of the galaxy. Don't look at the star that's right above the magnitude label. Look inside the disk, and you'll see that there is one star that's actually getting brighter and brighter with time, and then fading with time. And so we see that as time goes on, this particular star is getting brighter and brighter and brighter and then fading. So we definitely see the star getting brighter as time goes on. And that was in January of 2014. And I remember taking out a telescope, and when I looked at that thing, I could definitely see a line of 3 stars. I could see the 2 stars, and it's most obvious in the lower left-hand corner of this image, as well as the core of that galaxy. So this was eminently within the observational capacity of a 15-inch telescope in an urban environment. I saw it. And there's another image. This was taken by a micro-observatory, and we see all the way over on the right. There it is right there. There's the supernova in M82. Here's another supernova in the galaxy NGC 1309, and there's a Hubble follow-up image with respect to it. The left-hand one, taken by the Lick Observatory, was in 2002. And once you run out of letters, you start doing 2 letters. So they went through the entire alphabet, and that's because F and K. What does F and K mean? Well, there's been, since 1994, serious supernova studies, so people are able to find large numbers of supernova by going and hunting for them. So dedicated supernova searches have found hundreds a year. And we see in the Hubble image from 2005, they're able to pinpoint exactly where that star was in the sky and try to look for remnants. And finally, let's look at the nature of what a supernova explosion kind of looks like. They're very, very, very luminous, and we talk about light curves, and that's why we have these images that we looked at before, is that how does the luminosity of such a star change with time? And there's two types, two general types. There are many, many, many subclassifications, but I'm just going to keep it with these two types because it makes it a little easier to understand, because there's two principal versions of supernovae. And we're really only talking about one kind this time, which is called core collapse supernovae. And a core collapse supernovae is called a type 2 supernova, and that's the green line in the background. What you see is that there's an incredible brightening, and then it dims for a while, and then it has a plateau, a flat plateau for a while, where it stays at roughly the same brightness for a long time, maybe a month or so, and then dims again at kind of a curve, and then the curve changes shape again. Each one of those changes of curvature is a result of different material glowing. So the initial brilliance of the supernova will fade over time, and it's slow because all of the gamma rays, remember that supernova explosion had all sorts of things mixing down right above the core. And that means there was a huge amount of nuclear fusion that occurred explosively in the core, and rather rapidly. So in that explosion, it created large numbers of radioactive elements, and this primarily radioactive nickel and radioactive cobalt. We see that there is a decay of radioactive nickel to cobalt to gamma rays. Those gamma rays then illuminate the gas that surrounds the supernova and makes it glow, because the gas, it might be too thick to actually let the gamma rays come straight out. The nickel tends to be the thing that fades out more slowly at the top, and cobalt is primarily responsible on the right. So there are also these two types of supernovae, not just their light curves, meaning one just gets bright and then slowly dims, that's the type 1s. The type 2s have a slightly different appearance to them. Type 1s have no hydrogen line emission features, but type 2s do. And that makes sense that a type 2 supernova would have a lot of hydrogen line emission. Remember, hot hydrogen gas happens because it gets really hot, right? And so the atom gets ionized or excited and drops back down from excited states down through. So you get hydrogen emission lines in visible light. And so you should see that pinkish glow of hydrogen, or at least an emission line looking at the spectrum. That's because the outer 5 astronomical units of the star, or a significant fraction of the star, did not participate in the fusion down in the core. So it's still hydrogen. So type 2 supernovae have hydrogen emission lines, but strangely enough, type 1s don't. So core collapse supernovae are the type 2s. They do have significant hydrogen absorption lines, but type 1s don't, which is really interesting. So let's look at one in particular, one of the more recent ones that came out that happened when I just got done with high school. So when I was in high school in 1986, I graduated and went off to college and started studying astronomy, and everybody all of a sudden started talking about Supernova 1987A, the first one in 1987, in February 23rd. And that happened in the Large Magellanic Cloud, and the Large Magellanic Cloud is a neighboring galaxy to the Milky Way. It orbits at about 160,000 light years away. So for a very short period of time, it was brighter than 5 billion suns, which is amazing. Finally, which made this really important, we haven't had many Milky Way-based supernovae. And now the Large Magellanic Cloud is not part of the Milky Way, and the Large Magellanic Cloud is outside the Milky Way, but we haven't seen many naked eye supernova since Kepler saw one in 1604. So this is the picture that was taken by the Anglo-Australian Observatory of Supernova 1987A. The right-hand side shows before, and since it's in the Large Magellanic Cloud, and that's a close-by galaxy, this is an extraordinarily studied area. And because it's so well studied, there's lots of pictures, and people were able to determine exactly which star it was before it exploded. And there's the star. And we can see there's the Large Magellanic Cloud itself in the sky. It's a star forming region. It's a huge star factory. And then we take a slightly different view of it from an emission line survey on the left-hand side. And then we show where this location is in Anglo-Australian Observatory's image of it. And then we see a Hubble Space Telescope image of it being close up. So here's some of the vital statistics for 1987A, which was a supermassive star. It has a funny name named after the guy who actually made a catalog of these large stars, these hot stars in that area. Large Magellanic Cloud, distance about 50,000 parsecs. And the type of star was a B-type star, a B-type supergiant. So it's not as hot as an O star, but it definitely is a hot blue star. And the size of the star before it exploded was about 50 times the radius of the sun. The surface temperature was about 16,000 Kelvin. Remember, the sun is 6,000 Kelvin. So the surface temperature wasn't as was just only a little bit hotter, only 3 times hotter than the surface of the sun. However, the core was a different matter. The luminosity of that star prior to its explosion was over 100,000 times the luminosity of the sun, and its mass was about 16 times the mass of the sun. Now, there was another really interesting thing that happened at this exact time that the star went off. A neutrino burst was detected. There were 19 anti-electron neutrinos detected by the various neutrino observatories across the world. The Kamiokande Observatory, which is in Japan, observed 12 of those 19. And the energies of these neutrinos were about 20 mega-electron volts. Remember, the binding energy of the core of a nucleus is about 8 or 9 for iron nuclei. So these neutrinos were given almost 3 times the energy required in order to rip apart an atomic nucleus of iron, which was fascinating. So there was a huge amount of energy being pushed into neutrinos as the star was collapsing in the core. The thing that made it really interesting and this star began the process of what's called neutrino astronomy, because they were detected 3 hours prior to the light of the star. The star was observed by an astronomer because it was up at night, and it was seen in the sky at night. And he reported it the time he saw it, and he swung a small telescope over to take a picture of it when it was observing down in Australia. But because the distance to it is 168,000 light years, and because we detected 19 antineutrinos across the Earth, that meant, because of how seldom and how rarely neutrinos interact with normal matter, there had to be 50 billion neutrinos coming from supernova 1987A, arriving at Earth, at the Earth's distance from it, 168,000 light years away, 50 billion neutrinos per square centimeter. So hold out your thumbnail, that's about a square centimeter, and at that moment, 50 billion neutrinos passed through your thumb at that point from that one supernova. That meant the total number of neutrinos that was emitted from this explosion was about 10 to the 58th. That's a big amount of neutrinos. That's a 1 with 58 zeros after it. I didn't even bother to write it out because, it'd be cute and everything, but who wants to do that on this thing? And the neutrino burst lasted about 10 seconds, which lends credence to the idea that the neutrinos get all bunched up. And there were actually 2 or 3 waves of neutrinos that occurred. The total energy released in the neutrinos is about 10 to the 48th joules, which is about 10 to the, if you add it up over 10 seconds, that's 10 to the 22nd times the luminosity of the sun. That's a lot of energy. In fact, 99%, more than 99% of all of the energy of supernova 1987A and all core collapse supernovae go out in the form of neutrinos. Neutrinos carry away almost all the energy. Sure, we can see it as a bright thing. But if we could look at if we had neutrino detecting eyes, we would be blinded because there would be too many neutrinos for us to see. And the luminosity of it was astonishing in terms of how much luminosity there was in energy compared to the sun. So the peak visible luminosity, meaning how much light it emitted, was about only a measly 4 times 10 to the 33rd joules, which is only 100, which is only about 10 million solar luminosities, which isn't much. So that's incredibly small compared to the neutrino luminosity. It's a tiny fraction. Remember, you subtract, that's about 10 to the 15th times less luminosity in light than there was in neutrinos. Well, the material that got ejected really hard at 10 to the 7th meters per second. That's about 3% the speed of light. And about 4 solar masses of material got ejected from this supernova. And it imparted 10 to the 44th joules of energy. So the kinetic energy of the material is comparable, or at least it begins to be comparable, to the total energy released in neutrinos. So the kinetic energy is about 1/100th of 1% of the neutrino energy. And just to give it a reference frame, it became as bright as a 3 magnitude star. So it was pretty bright. So if you were down there, you could say, hey, what's that new star in the sky? Because a 3rd magnitude sky under dark sky conditions, and if you know your night sky, you'd say, that's a new star. You would have noticed it. It is a distinctly noticeable star. It wasn't as bright as like -2, like Venus or something, but it was as bright as one of the stars in one of the belt stars in Orion. That's as bright as that. Or one of the brighter stars in bright constellations, such as those in the Big Dipper. So it became pretty bright. It was definitely naked eye star. But remember, most of the energy was not in light, wasn't even in ejected material. Almost all of it was in the neutrinos. However, that doesn't stop people from looking at stuff. And what's really neat is the American Association of Variable Star Observers had a number of people who went and took a look. And what we see is this is the light curve from visual observations of supernova 1987A. And this is in the V magnitude, and we see people making magnitude measurements over the course of time. And this can be downloaded from avso.org, and it shows that it was caught before the peak occurred, then the peak occurred, and then it had a plateauish sort of long slope, and then it had another drop off. So the first peak, when it was observed, was the initial explosion, and then it got brighter as time went on because nickel 56, which is radioactive, decays to cobalt 56, and which is also radioactive. So the nickel has a very short half-life, and that's the first decay of the curve, and it got brighter because that stuff was seen. As the shroud of gas was revealed, it got brighter and brighter and brighter. So the first slope down is the dimming as the nickel 56 finally decays and becomes cobalt 56. Then that drops away. There's not much nickel 56 left. We got a bunch of cobalt 56, and so we got this longer, slow, slanted curve, and that shows it decaying to normal iron 56. So iron 56 is the most common thing in the universe because everything more massive than it, or at least many of the products that would be formed in supernovae, decay to iron 56. And then it kind of has a nice little curve at the bottom, and that's just the remaining gas and dust being heated by X-ray emission from residual things as well as shock heating from around. And it got dimmer and dimmer and dimmer. And once it got below magnitude 6, it was below naked eye view, and then people were using telescopic views all the time. So that's really interesting. And we see how long it takes for these things to go. And you can see that it was observed in February, and it was a big burst of observations right there, as people ran to their telescopes in order to make these strong observations. And if you went to the AVSO website, you'd see how many people actually participated, which is a lot. So later on, we see images of rings surrounding supernova 1987A, and the bar shows the angular diameter, which is 1/60th of the angular diameter of the moon, which is about one half of an arc minute. So that shows it's not very big in the sky, but at least it's noticeable in a small telescope. So when this was looked at, it was determined by subsequent Hubble observations that this glowing ring exists. These rings, that really bright ring in the center, has been there for about 20,000 years before the star exploded. And when the X-rays from this explosion energized all the gas, it's making it glow. And all these things, these blobs, are moving really fast, moving at about 20 million miles an hour, and that creates a shock wave of material that slams into, and that shock wave of material heats it up and makes the material in the surrounding medium, the surrounding interstellar medium, glow. So there's the glowing material moving at millions, at tens of millions of miles an hour, slamming into the interstellar medium and causing it to be hot and emit X-rays. And there's also these kind of interesting bubble shells as well, which are like light echoes. And we can see that the Hubble Space Telescope imagery from 1994 to 2003 shows the evolution of this ring. The initial ring was heated by X-ray emission, and then as time went on, the material from the supernova slammed into that hot ring and made it glow brighter. And there we see a detail. There we see a brighter detail showing the knots of hot gas that's been heated to tens of millions of degrees. It also emits X-rays. And how did this actually come about? What's different about this? And we're going to go into this a little bit later too, but let's look at how supernova 1987A might have arisen and where those rings came from. Probably the star was a binary system, and the more massive star evolved first, became a red giant, and as it became a giant, it literally engulfed its close companion. So these two were incredibly close stars, and then the two stars, one star got larger and larger, and that provided drag on the other star. Third, the two stars, in so spinning, most of the star, the red giant, got pushed out into a spinny envelope to conserve angular momentum as one part merged and the other part expanded away. So then you have this ring that's been expanding away as the two stars now merge together into one. Then as they merge, you have basically something that's very similar to a protoplanetary disk like we saw in the interstellar medium stuff. And that's what the bipolar outflows of gas made this ring-like structure in the bubbles above. Finally, then, there's a massive explosion that occurs, and that's the supernova that we saw, all in bright light. And then the ejecta start to move outward, and once the ejecta then from the supernova slams into the disk, it makes it glow and forms those beads. So there's the story of how people think it actually worked. And so you have all these knots of gas and dust. There's bipolar flows, meaning that's what that inner glow is about, from the jets that occurred from the supernova as the material flows outwards. So there's some hot material sitting there. And yet, this should have formed some sort of neutron star or black hole, but it isn't seen yet. And it basically has not been revealed yet because the gas density might be too high. There's no reason to think that it's not there yet. It's just hidden for some reason. Maybe it got ejected and shot out to the left or something like that and left the entire area. But there should be some kind of disruption if it did that. And angular momentum would say that it would probably be shooting off into the ring structure around it. Anyway, we see that there's a pretty interesting explanation for those fun ring structures of supernova 1987A, which was the nearest supernova to us since 1604. And why we care about supernovae, and we're getting close to the end here, so bear with me, is because nucleosynthesis is where we get all of the elements in the cosmos. We start the universe with hydrogen and helium. The Big Bang made hydrogen and helium, but stars make everything else. The iron that you use that is in your blood was formed in a star. The nickel that you pay a piece of candy for at the nickel and dime store, that was made in the center of a star. The universe started out with about 75% hydrogen, just under 25% helium, and little bits of lithium, boron, and beryllium, but nothing else. Every other element were fused in nuclear reactions inside of stars, and all heavy elements above iron are formed in supernova explosions of various kinds. So the 10 most abundant elements in the entire universe are hydrogen, helium, starting at the top, all the way down to sulfur and magnesium. And notice what's interesting about what we see in the topmost 10 abundant elements is that many of them, like magnesium, carbon, oxygen, nitrogen, iron, those things are really important for life. So the elements that make up life are incredibly common elements in the cosmos, and they're also small on the periodic table. We also see silicon being a very large amount that was formed. And notice what the Earth's crust is made out of mostly, primarily silicon oxides. And so that shows where planetary objects come from. So planets are made from silicon and iron predominantly, with all sorts of other stuff and carbon and oxygen, and life uses those common elements in huge amounts in order to metabolize and live. So what happens to that supernova remnant, such as 1987A? Well, you get all sorts of all the materials that were made in that, all that fusion enriched stuff was made in the explosion. It expands at thousands of kilometers per second. That makes a blast wave. As we saw with 1987A, it plows into the interstellar medium. It stirs the interstellar medium. It makes an ionized nebula that can be seen for thousands of years. We'll talk about supernova remnants next time. But that makes something to be seen for a few thousand years after the explosion. And that material then mixes with the interstellar gas. That mixed gas becomes part of the next generation of stars with these metals, and then the next stars are more metal rich. And by metal, I don't mean like iron and nickel and so forth. I mean any other element heavier than helium. That's what astronomers call metals. That's a really funny thing. So metals are things that are heavier than helium, and all successive stars have more of it as a result of that. So the material that was formed in those supernovas goes out into space, and all of the things that are us that were formed in some supernova long time ago in the same galaxy. And therefore the solar system itself formed 5 billion years ago by gas that was enriched from these massive star explosions. And so stars form, they evolve, they live, and they die. And then they push out that stuff into the interstellar medium and make more stars. And that's what we mean by this thing that we saw earlier on, that this beginning stars start from clouds of gas and dust. They form protostars. They go through their main sequence lifespan. They then become red giants or explode as supernova. If they become red giants, they puff off their outer layers as planetary nebula. The more massive red stars, like a little bit more massive than the sun, churn out a lot of carbon before they do that. The most massive stars go into these core collapse supernovae and explode wildly in order to make these type 2 supernovae. Sometimes they'll form a neutron star, and sometimes they'll form a black hole. The most massive stars at the top of this thing can go straight to a black hole, and that's really interesting. And we'll talk about those when we talk about gamma ray bursts. But for now, notice the cloud on the left forms stars that are protostars, and stars become that way, and they shed their outer layers or explode or something like that, and seed the right-hand side of this, which is more and more and more gas and dust. And that then loops around to the left, with those small mass stars at the bottom and the high mass stars on the top, with 80% of all the stars in the Milky Way just brown dwarfs and red dwarfs, with the rarest of things, the tiniest sliver of stars become blue giants, blue supergiants, and explode violently in these ways to make supernovae. All right, so that's more about supernovae, and we'll be talking about their remnants next time. See you soon.